In this video, we're going to talk about the reaction quotient Q. We had already talked about the equilibrium constant K, which is found by taking the ratio of concentrations of products and reactants at equilibrium. When considering Q, it's almost the same thing, except the reaction doesn't necessarily need to be at equilibrium when you plug in concentrations. The reaction quotient is calculated the same way as the equilibrium constant. Products raised to the power of their coefficients, all over reactants raised to the power of their coefficients, except that it uses concentrations that are not known to be at equilibrium, which we call initial concentrations, instead of concentrations that are known to be at equilibrium, which we call equilibrium concentrations. The reason we calculate Q is so that we can draw a comparison between Q and K and thereby determine in which direction the reaction will shift. What that means is, are you going to make more products in order to reach equilibrium, or do you need to make more reactants in order to reach equilibrium? Answering that question is really important for a chemist who has to sit around and figure out what are the ideal conditions under which I need to make a reaction go. If you know that you're making more products and you know that the products have a certain set of conditions under which they form more readily, you would want to make sure that those conditions are met as you're performing the reaction. There are three possibilities when you make the comparison of Q to K. If Q is equal to K, then your system is already at equilibrium. There's nothing that needs to happen in order to reach equilibrium. Take a look at this chart below with the Q, which is the pink bar, K, which is the blue bar. If they're equal to each other, you're already at equilibrium. Another possibility is if Q is greater than K. In that case, to reach equilibrium, we need to shift left. Take a look at the pink bar. Right now, it's more than K. The K bar only goes up this high. So to reach equilibrium, we need to shrink the value of Q until it equals the value of K. That's when we know we're at equilibrium. The system, if Q is greater than K, currently has excess products, and those product molecules need to react away before you reach equilibrium. The third possibility is if Q is less than K. Take a look at the height of the pink bar in the picture on the left as compared to the blue bar. Furthermore, notice that the blue bar is constant throughout, right? The equilibrium constant is the same, but the value of Q can change. If Q is less than K, the system currently has excess reactants, meaning you've got to react away the reactants. They've got to become products before you can reach equilibrium. There is a little thing about terminology and formatting that we should address before going forward. When I say initial concentration, I mean that it's a concentration for a chemical that is not known to be at equilibrium. And in terms of formatting, we distinguish initial concentrations from concentrations known to be at equilibrium by adding a non-mathematical subscript 0. So for example, if I put HCl in brackets and then put a non-mathematical subscript 0 outside the brackets, I'm referring to an initial concentration. There's no mathematical meaning to that 0. It doesn't mean raised to the 0th power. It doesn't mean anything other than what the way chemists typically had denoted that in the past is if you're plotting concentration against time, and at the very left edge of the graph, that's time equals 0. That's why they put the 0 there. It's like when time equals 0, the very first concentration that you record, you don't know that it's at equilibrium. It might work out to be at equilibrium, but it's not known to be at equilibrium. They put the 0 there. Whereas an equilibrium concentration is simply the substance's formula in brackets. There's no, if anytime you see a substance's formula and brackets and no notation outside the brackets, then you have to assume it's an equilibrium condition. So if we just write it like this, then it's known to be at equilibrium. If we mean an initial concentration, we've got to put in a non-mathematical subscript 0 outside. Okay, let's consider the balanced equation. 2NO2 yields one single product molecule, N2O4. Let's say that we're tasked with writing the equilibrium constant K and the reaction quotient Q. A chemist is studying this reaction. She doesn't know the value for K beforehand. She measures the concentrations of the NO2 and the N2O4 at various times after the reaction has begun. We're going to take a look at a series of pictures. In these pictures, when you see red spheres, that represents an oxygen atom. When you see a blue sphere, that represents nitrogen. Now, if our reactant is NO2, then NO2 is going to have one blue sphere and two red spheres. And the product N2O4 is going to have two blue spheres and four red spheres. Okay. Here's our first picture. The picture below represents reaction conditions when the experiment first begins. Look at the picture to determine the concentration of NO2 initially. Notice the non-mathematical subscript outside the brackets. And the concentration of N2O4 initially. Then calculate the value for the reaction quotient Q. Here's our initial picture. So if it's a red sphere, it's oxygen. If it's a blue sphere, that's nitrogen. Look at all of these clusters of atoms. Every single one of them consists of one blue and two reds. They're all NO2. And if I were to count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the concentration of NO2, I would have to say, is 10. The concentration of the product, N2O4, since I don't see any of them, would be 0. We calculate Q the same way as we calculate K. If our equation was 2NO2 yields N2O4, take the product concentration divided by the reactant concentration raised to the power of its coefficient 2. But you also add the non-mathematical subscript 0 outside the brackets. And if after studying this picture, we've determined that the concentration of N2O4 is 0 and the NO2 is 10, that means we would calculate Q by taking 0 over 10 squared. Well, that's equal to 0. Okay. Our reaction quotient for this picture, that it represents a slice of time, Q equals 0. Let's consider another one. The chemist continues to study the reaction, and she waits 5 hours and takes a sampling of the molecules in the reaction vessel, and this picture is going to represent that. Again, we're going to calculate Q. Notice this time we've got one of the product molecules. See the big molecule towards the bottom that consists of 2 blue spheres and 4 red spheres? That's the N2O4 molecule. There's only one of them. And there are 1, 2, 3, 4, 5, 6, 7, 8 of the reactant molecules NO2. So at this point in time, our concentration of NO2 is 8, and our concentration of N2O4 is 1. We'll calculate Q the same way as we calculated K, and the same way that we calculated Q earlier. The product molecule concentration is 1. The reactant molecule concentration is 8. So it would be 1 over 8 squared. That's 1 over 64, which on your calculator, if you want to type that in, as a decimal, that's 0.016. Okay. Good. Let's do again. Now we've waited 10 hours. And again, we're going to show a picture of the molecules present. How many of the big product molecules do you see now? See 2 at the top and 1 at the bottom? That's a total of 3 of the big product molecules. And there remains 1, 2, 3, 4 of the smaller reactant molecules. So the concentration of NO2 is 4, and the concentration of N2O4 is 3. We'll calculate Q the same way as we did earlier. The product concentration over the reactant concentration squared, which in this case would be 3 divided by 4 squared. That's 3 over 16. If you want to punch that in the calculator, that's 0.19. Notice that our value for Q is increasing. We went from 0 to 0.016 to 0.19. Okay, one more picture. I don't want to bore you to death here, but it's good to get at least one more in for thoroughness sake. Now the chemist has waited 20 hours. So another 10 hours after the previous picture. And here's what we've got. 3 of the big molecules and 1, 2, 3, 4 of the smaller molecules. That's the same as the last time. N2O4, concentration of 3. NO2 concentration is 4. If we calculate Q the same way, that would be 3 divided by 4 squared, which is 3 over 16. That's 0.19, the same thing as before. Okay, let's summarize and try to make sense of this. At 0 hours, when the reaction first began, there were no products. That's often the case when a chemist is running a reaction. He or she puts nothing but reactants in the reaction vessel. And we calculate Q to be 0 at that point. 5 hours goes by. We've produced 1 product molecule. There still remains 8 reactant molecules. At that point, Q equals 0.016. Notice that Q is going up. 10 hours goes by from the beginning. There are 3 of the big products, 4 of the original smaller reactants. The value for Q now is at up to 0.19. Another 10 hours goes by and the value for Q has not budged. It remains at 0.19. All right, let me ask you a question. Use common sense, please. What's the value for Q at equilibrium? If you waited 10 hours and arrived at a value of 0.19, you wait another 10 hours and it's still 0.19? Hey, that's the value for Q at equilibrium. And if it's at the value for Q at equilibrium, that means that Q and K are equal to each other, which means that that's your value for K. Oh, man. So Q and K at equilibrium are equal to each other. And in this particular example, that value is 0.19. Let's try a problem together. Try to put all of this into one problem. K equals 2,400 for this reaction. A chemist measures the following amounts of species. Is the reaction at equilibrium? Yes or no? If not at equilibrium, in which direction will the system shift in order to reach equilibrium? Here's your balanced equation. 2NO yields N2 and O2. Now, the chemist puts the reaction together thus. She puts 0.090 moles of NO, 1.8 moles of N2, 1.6 moles of O2, all together in a 3-liter flask. How are we going to deal with that information? Well, we've got a number of moles, and we've got a number of liters. Let's calculate the molarity, the initial molarity, and I'm putting this non-mathematical subscript 0 outside the brackets to indicate initial molarity for each one of the species that we have information for. In the case of N2, and by the way, I'm using the molarity formula, which hopefully you remember, moles divided by liters. We have 1.8 moles, and they said it was a 3-liter flask. If you divide that out, that's 0.6 molar. So our initial concentration of N2 is 0.6. For the O2, let's see, 1.6 moles in a 3-liter container. Divide that out, we get 0.53 molar. And for the NO, they tell us we have 0.90 moles. I'm getting these numbers from over here in a 3-liter flask. And that works out to be 0.03 molar. Let me clarify this. This is 0.53. Okay, so now we've got initial molarities for all of the substances in this equation. Let's write the expression for the reaction quotient Q. Remember, it's calculated the same way as K, except you get to use initial concentrations. So that means take the products, put them in brackets, and multiply them together. So we're taking product concentrations times each other. And if there were coefficients, you would have to raise these concentrations to the power of their coefficients. In the denominator of the expression, we're going to put the concentration of the reactant, NO. There's only one reactant here. And notice that the coefficient 2 comes into the expression as the exponent. And also notice that every single one of these substances concentrations has a non-mathematical subscript 0 outside the brackets. Now let's plug in. We've calculated these concentrations, 0.6 times 0.53, all divided by 0.03, and that concentration in the denominator needs to be squared. So punch on your calculator, 0.6 times 0.53 divided by 0.03 squared. And I get a value of 355. Now, you might say, okay, we did a whole bunch of work here. What's the point? The point is we're going to make a comparison between the value for Q and the value for K. Which number is bigger, 2,400 or 355? We know that K is 2,400, and we know from all the information that we were given and some calculation that we did that Q is 355. Well, students, obviously 2,400 is the bigger number. So that means that K is bigger than Q, or you could say Q is less than K. It's the same thing, right? Q is less than K. And so if you look at the bar chart, let me draw this real quick. This was like the picture on the left side where K was a certain height and Q was less than that. And in order to reach equilibrium, where the two bars are the same height, we've got to shift to the right. That means we need to make more products in order to reach equilibrium. What would that do mathematically? Consider how we calculate Q. It was product concentrations divided by reactant concentrations. If we make more products, then as time goes on, the value of the numerator in this ratio is going up. And simultaneously, in order to make products, you have to consume reactants. So that means that the concentration of the reactants is going down. The value of the denominator is shrinking. When you think about ratios, increasing the numerator or decreasing the denominator increases the value of the ratio. And here, both are happening at the same time. It's kind of like in the previous question where we had the pictures. The value for Q was slowly increasing until eventually it leveled off. Here, in this problem, they gave us a value for K, and they gave us enough information to calculate a value for Q and make a comparison. Well, we made the comparison. Q is less than K. We need to make more products before equilibrium is reached. As to how long that takes, well, that's a whole other question. In fact, there's a whole domain of chemistry devoted to the length of time that it takes a reaction to proceed. It's called reaction kinetics. Good luck with the homework.